Okay, in this video I'd like to introduce the combined gas law. And as the name implies, this is a law that combines three of the individual gas laws into one equation that relates three of the fundamental properties of gases: pressure, temperature, and volume. So, from previous work, you may recall that one of our gas laws, the Ch8 law, was that pressure over temperature was equal to some constant, and we'll call that constant Q for now. That was the Ch8 law. In addition, we had Boyle's law, and Boyle's law showed the relationship between pressure and volume, and so we had pressure times volume equals some constant, and we'll call that lowercase r for now, just some constant there. And a third individual gas law was Charles' law, and Charles' law related volume and temperature of a gas through this relationship: volume divided by temperature was equal to some constant, and we'll just call it S for now. So if we take those three individual gas laws, we can combine them into one relationship. So we can say pressure over temperature, and we get that from the Ch8 law. And then we combine it with this law, the Boyle's law. So pressure times volume in the numerator there. And we'll also see that Charles' law is implied in this: volume in the numerator over temperature in the denominator, V over T. So all of that together equals some constant, and the constant is the addition or the combination of the three individual gas constants, and we're going to call it, temporarily, we'll just call that some constant K. So this is a combined gas law by combining three of the individual gas laws, and it shows how there is a relationship between pressure, volume, and temperature, and that they are all related to some constant K. Now, the most important use of this for our purposes is when we are dealing with a change in gas conditions. So we are going to take advantage of the fact that this relationship remains constant for a gas. Regardless of whatever happens to any of these properties, this relationship will remain constant. So what we can say is the initial pressure, the initial volume, and the initial temperature of a gas, which we'll represent by these subscript 1s. So the initial pressure times the initial volume divided by the initial temperature of a gas must equal that constant, and since that constant is constant, then this relationship will hold even after the change has taken place. So they will equal the final pressure times the final volume divided by the final temperature. And so since the initial set of conditions equals that constant, and the final set of conditions equals that constant, then we can just say that the initial set equals the final set. And this is one of the forms of the combined gas law. Yes, you can have a combined gas law that just has the pressure, volume, temperature, and that K constant, but for our purposes, we are mainly going to be interested in the combined gas law as it compares initial sets of conditions to final sets of conditions. Now, we can also include Avogadro's law in here, and we know as Avogadro's law has a relationship with volume in the numerator and number of moles of gas in the denominator. So we don't have to include that, but I will go ahead and include it. So the initial number of moles of gas and the final number of moles of gas. And so this is the complete form of the combined gas law. P1V1 over N1T1 equals P2V2 over N2T2. There are 8 variables here, and this equation is the form of the combined gas law that is especially helpful when we are considering the change in properties or variables of a gas from an initial set of conditions to a final set of conditions. We don't generally use this equation when we are running a chemical reaction. So this is for a change in conditions, not for a reaction. Now, these values, pressure, volume, number of moles of gas, and temperature. Now, these variables represent properties of a gas, the pressure, volume, moles, and temperature of a gas. And in this form of the equation, we must always remember that temperature must be in kelvins. So temperature is in kelvins. The lowercase n is the number of moles of the gas. V is the volume of gas in liters. And P is the pressure of a gas. And that can be given in atmospheres, millimeters of mercury, torr, as long as they are used in the same units of measurement on both sides, then it doesn't matter what unit of measurement the pressure is in. But we absolutely have to have kelvins for temperature. Okay, now there are 8 variables here, and that's a lot going on in this equation. Generally, the way this equation will be more useful to us is if we can simplify the equation so that we don't have as many variables. And the key to being able to simplify this equation is right here. So notice that if one of these variables is held constant, it can be eliminated from both sides of the equation to simplify the equation. So let's see what that means. If, for example, the number of moles of gas does not change from its initial to final conditions, that means that this N1 equals this N2. And if N1 and N2 are equal, then I can cancel them out on both sides of the equation, and the equation is still true. Remember that if you do the same thing to both sides of the equation is still valid. So we are going to be looking in our problems for when we can cancel out terms from this equation and simplify it. The assumption we will make is that if one of these variables or properties is not mentioned in the problem, then we will assume that that property is being held constant. And so we're going to read the problem not only for what is explicitly stated, but also for what may not be in the problem, because that is also going to give us valuable information. Now I'll make one more comment here. There is a gas constant, and this K is not the gas constant, because this K represented the constant that I got from adding the individual constants from just these 3 laws. Once we add Avogadro's law in here, and we include the number of moles of gas, then the constant that this equals the gas constant R. And we'll talk more about the gas constant R. But for now, I'll just point out on the back of your periodic table, we've given you the value of R. So for gas law problems, if we ever need to use the gas constant R, we will be using this value and not this one. Now, in the sample problems that I'm going to be giving you for the combined gas law, we are not going to need to use the gas constant R. However, in our next topic, we're going to be dealing with the ideal gas law, and that does have the gas constant R in it. So that's just a little bit of foreshadowing to let you know that we are going to see a constant, but it's going to be the gas constant R. So let's move on and see if we can do one of these sample problems as a combined gas law problem. So here I've got sample problem A. This sample problem, it says calculate the new volume, so the final volume, right, and there's a volume of a gas. So this volume must have been an original volume, and I'm going to calculate a new volume, or a final volume of a gas. So it looks like this is my V1, my initial volume, and this is my final volume. So we're being asked to calculate the final volume, or the new volume, of a gas that originally occupied 2.0 liters. If its temperature is increased from this temperature to this temperature. So if it increased from 21 degrees, this must have been my initial temperature, and that must have been my final temperature. So right away, I can say I'm dealing with a gas here. I am not running a chemical reaction. All I'm doing is increasing the temperature on this gas. So I'm going to use the combined gas law. So I'm going to write the combined gas law here. P1 V1 over N1 T1 equals P2 V2 over N2 T2. Okay, there's my combined gas law. And my goal here is to see how I can simplify that so that I'm not dealing with 8 variables. Well, how am I going to do that? Well, I look at the problem that is given to me, and I look to see if any of these properties of a gas are not mentioned at all. And if they're not mentioned at all, then we make the assumption that they are held constant. And if they're held constant, then we can cancel them out on both sides of this equation. So notice it talks about the volumes and about the temperatures, but it never mentions anything about the pressures or the number of moles of gas. Nor does it mention anything about the grams or mass of the gas, so I wouldn't be able to determine its moles. So both the moles and the pressure of this gas seem to be held constant. Well, if the pressure is held constant, then I can eliminate it from both sides of the equation. If the number of moles of gas are held constant, then I can eliminate that from both sides of the equation. And by doing this, you can see that I have simplified my equation. I went from 8 variables, now I only have 4. And in doing so, I can see that the variables that are left, V1 divided by T1 equals V2 divided by T2, and that is Charles' law. And you notice that I have been able to derive Charles' law without having to memorize it. All I did was I knew what my combined gas law was, and I knew how to simplify it based on the assumptions of which properties were held constant. So here I've regenerated Charles' law. I'm going to rewrite it just to give myself some space to work with it, because I'm going to have to rearrange this equation slightly. So there's the equation right there, V1 over T1 equals V2 over T2. I've just rewritten it right there. Well, I've got to rearrange this equation algebraically to solve for the unknown. What is the unknown? It says to calculate the new volume, V2. So it's V2 that I'm looking for. I'm going to calculate V2, so I need it alone by itself. And to get it alone by itself on the side of an equation, it has to be in the numerator, which it already is. And then I have to eliminate everything else that's with it. Right now, the T2 is with it. T2 is in the denominator. So to get rid of it over here, I have to multiply both sides by T2. That cancels it out there. If I do it over here, I have to do it over there as well. T2 as multiplying. All right, so now I have my V2, that's the variable that I'm looking for, equals T2 times V1 all over T1. So I'm going to rewrite that here. So I've got V2 equals T2 V1 all over T1. So now I'm very close. I've identified my equation, I've rearranged it to solve for the unknown, and now the only thing that I have to do is I have to plug in these values and I'll have my answer. So let me get started here. So what is T2? It's right here. But notice this is in Celsius, and I cannot use degrees Celsius in gas laws. Why is that? Because Celsius is a scale which has negative values in it. You could have negative Celsius, and you can have 0 degrees Celsius. And if I have negative or 0 temperature, then look what that does to my equations up here. If I have a 0 in the denominator there, I can't solve that equation. If this is a negative number for temperature, then I end up getting a negative volume, which is impossible. You can't have a negative volume. You must have some volume or no volume. So the volume has to be 0 or some positive number. So the Celsius temperature scale does not work for gases. And it was because the Celsius scale does not work for gases, and the new temperature scale was devised so that you would never have a negative number, and it was theoretically impossible to ever get down to 0. And we now know that temperature scale as the Kelvin scale, which never has negative values and only has a 0 when you're at absolute 0, which is theoretically impossible because an absolute 0 Kelvin would mean that you had no thermal energy at all in a substance. So that's why we use the Kelvin scale for temperature in gases. So coming back to our problem here, we cannot plug in these temperatures until we convert them to kelvins. So let me do some conversions here. For T1, I have 21 degrees, and to convert it to kelvins, I have to add 273.15, and I get 294.15. But this is an addition problem, so the precision is dictated by that number, and so this is only 294 Kelvin. For T2, let's see, it's 55 degrees Celsius, and I have to add 273.15. I get 328.15, which again I have to round to the nearest ones column, which is 328 kelvins. So now I have my T1 and my T2 temperatures, and I can plug them in. So T2 is 328 Kelvin. V1 is right up here, 2.0 liters. All over T1, which is 294 kelvins. And if I do that math, I can see that the kelvins will cancel, and I'm left with liters, which is good because this is a volume. The math must be rounded to 2 sig figs, and the answer is 2.2 liters, and that's my answer. So my new volume, after I have heated up the gas, is now 2.2 liters. So that's how I set up the math, how I simplify my combined gas law to generate a simpler equation and, in fact, derive one of my individual gas laws, then rearrange it algebraically to solve for the unknown, and then start to plug in values, and with a temperature conversion to kelvins if necessary. Correct sig figs. Now, does this new volume make sense? Well, let's look at the temperature. If we look at kelvins and not Celsius, because Celsius will obscure the actual change in temperature. So let's look at the kelvins. It appears that when we go from 294 to 328, we have increased the temperature by about 10%. And we know that volume and temperature are directly proportional. So if we're increasing the temperature by about 10%, we should expect the volume to increase about 10% as well. And indeed, we went from 2.0 to 2.2, and that is a 10% increase. So not only does the math work out, but it makes sense. So that's how we set up and solve a combined gas law problem. Again, combined gas law problems are not for when you are running a chemical reaction, but only when you are changing conditions from one set of conditions for the gas to a new set of conditions for that same gas. All right, now I've got two more sample problems here that I'm going to ask you to do. So I would like for you to pause the video and work through both of these problems and get your answers. And when you have done both of them, then you can restart the video and I'll work through them with you. Okay, coming back from pausing the video, we're going to work through these two problems and see how you're doing. So for this next problem, sample problem B, it says to calculate the new temperature, so a new temperature of a sample of gas. And right there, this first phrase, calculate the new temperature of a sample of gas, that tells us that we are changing the temperature of a gas, and it's a big clue that we're going to use the combined gas law to solve this problem. So to calculate the new temperature, that would be the final temperature after the change, T2, of a gas at 475 torr. So there's a pressure. If its temperature was at that temperature, so that was the original temperature at that pressure. So that pressure must associate with the initial temperature. So this must be the initial pressure. And this must be the final pressure. So does that make sense? Calculate the new temperature of a sample of gas at this new pressure. Yes, that must be P2. Okay? This is a key skill to be able to solve a problem like this. You have to first recognize that you are changing the properties of a gas, and that means you're going to use the combined gas law. And then you have to be able to parse and analyze through the question and decide which variables in the combined gas law go with which values you are given, and particularly which value that you're looking for. So here it looks like we're dealing with temperatures and pressures, but nowhere in here does it mention the volume of this gas. And nowhere in the problem does it mention the number of moles of the gas. And so we're going to assume those were held constant, and that's going to allow us to simplify our combined gas law. So let's go ahead and write out the combined gas law here. We have P1 V1 over N1 T1 equals P2 V2 over N2 T2. Let's see if we can simplify it. Are there any variables that I can cancel out here? Well, it never mentioned volume, so I can cancel out the volumes. They are assumed to be held constant. And it never mentioned the number of moles of gas, so I can assume that they are held constant. So I'm left with an equation that is P1 over T1 equals P2 over T2. And notice what we've just done. Without having to memorize it, we have derived one of the individual gas laws. Which one was it? It was the Gay-Lussac law, or the Amonton law, where the pressure and temperature are related to each other. So this is the equation, the new derived equation that we're going to use to solve this problem. Well, first let's rearrange it algebraically to get it into the correct form to solve for the variable that I'm looking for, and that's T2. So I need to solve for T2. Well, to do that, I need to rearrange this equation so that T2 is alone by itself on one side of the equation. So it's in the denominator here, so the first thing I need to do is I need to get it in the numerator. And the way that we do that is we're going to multiply both sides by T2. And if I do that, it puts T2 in the numerator over here, and it cancels it over here. So now I have T2 in the numerator. So that's part way. I've got it in the numerator there. But now I need to get it alone by itself. So to get something alone by itself, anything else that's with it has to be eliminated. For everything that's in the numerator, you have to divide by that so that you can then cancel those out. If I do that to one side, I have to do it to the other side. And if it's in the denominator here, and I want to get rid of it, then I have to multiply both sides by that value to get rid of it. And that's T1 on both sides. Well, this looks kind of messy, but basically I now have T2 equals P2 times T1 over P1. Let's rewrite that to make that a little bit easier to see. So T2 equals P2 times T1 all over P1. Okay? Well, I'm almost there. I have my equation. It's rearranged to solve for the new temperature. And all I have to do is plug in values now. But I want to take a moment here and talk about pressures in the combined gas law. When we are using the combined gas law, yes, the gas constant R is given in liters atmospheres per mole kelvins. So you might think that we need to convert these pressures into atmospheres. And if you do convert the pressures to atmospheres, everything will work perfectly. But in combined gas law problems, you can leave the pressures in any sort of pressure unit. So torr is okay, millimeters of mercury is okay, kilopascals are okay for combined gas laws. If you don't want to have to remember which problems allow you to leave pressure in torr or millimeters of mercury or some other pressure unit, then you can go ahead and do the side math to convert those torr values into atmospheres. But in this particular case, in combined gas law problems, pressure can be in any unit, as long as it's the same unit for both pressure values. What cannot be left in any unit is the temperature. Temperature for gases must always be in kelvins. Let's take a moment to explain why that is. Early on in some of the early research being done on gases, when researchers were studying the interrelated properties of gases, the pressure, volume, temperature, and the number of moles, they found that as they were using the Celsius temperature scale for temperature, they would sometimes have a negative Celsius and sometimes have a 0 degrees Celsius, because those are possible on the Celsius scale. And look what happens to this whole equation if you have a 0 here. If you have a 0 in the denominator here for the temperature for Celsius, this equation cannot be solved. Another problem is if you had a negative temperature down here because you had a negative Celsius, then it would end up telling you that you had a negative volume, for example, of the gas. And that's physically impossible. You can't have a negative volume. You can't take up some negative amount of space. You either take up no space or you take up some space. So they found that the Celsius scale was not going to be useful for dealing with these gases. And so they came up with a new scale. And the new scale had to have no negative values, and it had to have only a 0 value when you had absolutely 0 thermal energy at all, which is theoretically impossible for a substance. And they call this scale after Lord Kelvin, who was one of the researchers in gases at the time. And so now we use that Kelvin scale. And the benefit of the Kelvin scale is that you will never have a negative value, and you will never have a 0 value for temperature. And so no matter what problem you're working with in gases, the temperature will always have to be converted to kelvins. If you want to be safe, you can convert the pressures to atmospheres. But in this case, we can leave it in torr. However, there are some cases where we will have to convert them to atmospheres when we deal with the ideal gas law, which comes after this. In this case, I'll go ahead and leave them in torr. So I'm going to solve for this new temperature now. And I'm going to plug in these values. The second pressure, the final pressure, 475 torr, times the initial temperature. The initial temperature is given in Celsius, so I need to convert it to kelvins. 0.0 degrees Celsius. I need to add 273.15 kelvins. And that's going to give me 273.15 as my answer. But notice my temperature was only precise out to the one place past the decimal. So my answer here has to be rounded to one place past the decimal. So that 5 means that that 1 is going to be rounded up to a 2. So my temperature is 273.2 kelvins. Okay. Now I can plug that in for my temperature, my initial temperature, 273.2 kelvins. All divided by the initial pressure. The initial pressure is right here, 345 torr. And I need to do some math here on my calculator. And my calculator gives me my answer that has to be in 3 sig figs, 376. What are my units going to be? Well, this is a temperature, and notice these torr cancel out, and it must be kelvins. So there's my answer. T2 equals 376 kelvins. So that's my final temperature. Well, let's make sure that this makes sense. So let's see. I have taken a gas, and it started out at this initial temperature, 273.2 kelvins. And I've increased it to some temperature. And it looks like that's an increase of about, I don't know, maybe 50% in temperature increase from 273 to 376. Not quite 50%, maybe 40% or so. Does that parallel the increase in pressure? Well, the pressure started out as 345 and it went to 475. So that looks like about a 40% increase as well. So as I increase the pressure, I would expect the temperature to increase, and they are increasing by about the same factor of about 40% or so. So this answer does make sense. Not only mathematically did it work out, but it also makes sense because we know that as you increase temperature, you also increase the pressure of a gas. Now let's move on to the last sample problem here. If you have already done this, then we're going to work through it now. If you haven't worked through this yet, or if you worked through it and you had some questions about it and you want to review your work, go ahead and pause the video now and then come back before you watch me work through it, just to see if you understand this. Okay, moving on, we're going to work on this last sample problem here. So let's take a look at it. It says a certain gas has a volume of 19.7 liters at a pressure of 745 millimeters of mercury. If the volume is increased to 22.5 liters, what is the new pressure of the system? And they're asking specifically in atmospheres. So let's see if we can assign variables to this. We can see that this is a gas that is changing conditions. So we are going to use our combined gas law. So I need to be able to assign variables here. It says if the volume is increased to, that means this is going to be my final new volume after the increase. So this is going to be my V2, my final volume. What is the new pressure? So there's what is the final or new pressure. That must mean that it has these volumes and pressures before the volume increased. So this must have been V1, and this must have been P1. All right, so right away we're thinking about how can we simplify our combined gas law. Are there variables that are not mentioned in the problem, and therefore we can assume they are held constant? Well, let's go ahead and write our combined gas law. So we have P1V1 over N1T1 equals P2V2 over N2T2. There's our combined gas law. Now, are there any variables I can cancel out? Because right now I've got 8 variables, and that's really difficult to solve this. Can we simplify it? What's a variable that is not mentioned in the problem so I can cancel it out here? Well, they talk about volumes and pressures, but they don't talk about moles of the gas or temperature. So I'm going to assume that those are held constant. And if they're held constant and they don't change, then they can be canceled out on both sides of the equation, both for moles of the gas and for temperature. So I end up with a simplified equation, and my simplified equation is just P1V1 equals P2V2. P1V1 equals P2V2. And look at that, I have derived Boyle's law, one of the individual gas laws, without actually having to memorize it. So we need now to rearrange this equation to solve for what? Well, they're asking me what is the new pressure, the P2. So I need to get this P2 alone by itself and in the numerator. Well, it's already in the numerator. That's already taken care of. So now I need to get it alone by itself. So I need to eliminate V2. And the way that I do that is I divide both sides by V2 so that it will now cancel that. If I do it to one side of the equation, I have to do it to the other side of the equation. And there we go. My simplified gas law, now that I'm going to be using, and now rearranged to solve for P2. All right, so I'm going to rewrite this over here to say P2 equals P1V1 over V2. And if I can just plug in values, then I will have my answer. So let's look at the pressure here. The pressure is in, the pressure is in millimeters of mercury. Now I could leave that pressure in millimeters of mercury right here, but when I finish this calculation, it would give me my answer in millimeters of mercury as well. And it's asking for atmospheres, right? So at some point in this problem, I'm going to need to do a pressure conversion. I can either convert this pressure now to atmospheres, so that when I plug it in there, it's in atmospheres already. And then when I get my answer, I'll already have atmospheres. Or I can leave this in millimeters of mercury now, and then get my answer in millimeters of mercury, and then at the very end I can convert that to atmospheres. Either is acceptable in this case. I'll go ahead and leave it the way it is for now. So I'll just go ahead and plug in 745 millimeters of mercury for the P1 right now. And then we'll deal with the atmosphere conversion later. Times V1. V1 is 19.7 liters. Divided by V2. V2 is 22.5 liters. And you can see how the liters will cancel and give me my answer in millimeters of mercury, and then I will have to convert that into atmospheres. So I'm going to have to do a little calculator math real quick. And the answer that my calculator gives me has to be rounded to 3 sig figs, and so that's going to be what units? Millimeters of mercury. Now beware, yes, you have answered what the new pressure is, but you have not answered the question entirely. You have not given it in atmospheres. So we need to make one more conversion here, convert from millimeters of mercury to atmospheres. So I'm going to say 1 atmosphere, 760 millimeters of mercury. And that's going to give me my answer. Let me do the math here quickly. And 3 sig figs, again, we're treating that as if it were exact. 3 sig figs, my answer is going to be in ATM. And that's my new or final pressure in atmospheres. Let's take a moment here to see if this makes sense. We started out with 745 millimeters of mercury. That's almost a whole atmosphere, right? So we started out at very close to 1 atmosphere. 1 atmosphere would be 760 millimeters of mercury. And we ended up with a pressure that is a lower pressure here. So the pressure has decreased. Does it make sense that the pressure has decreased? Well, let's look at the problem. The volume increased. And if you're increasing the volume of a gas, that means the pressure must be decreasing, because pressure and volume are inversely proportional. So it does make sense that the pressure must have decreased. And there's our answer. So before I move on, I just want to recap what we've done here. In a previous video, I showed you the individual gas laws and how these individual properties of a gas, the pressure, the volume, the moles of a gas, and the temperature of a gas, are all related to each other through proportionality constants. And because they're all related to each other by proportionality constants, we can get the combined gas law that relates the initial conditions of a gas to the final conditions of a gas. If we are given a gas which is changing conditions, not undergoing a reaction, just changing conditions, like for example, maybe I'm increasing the pressure on it, or maybe I'm increasing the temperature of it, then we can use the combined gas law. The combined gas law has 8 variables, though. So to simplify the combined gas law, to make it easier to solve, I can cancel out any of these properties that are not mentioned in the problem, and therefore they are assumed to be held constant. The result will be a simplified gas law that may indeed have given me one of the individual gas laws by derivation, by deriving it. Once I get that relationship, I then look to see what I am trying to solve for, and then I rearrange that equation algebraically to get that alone by itself on one side of the equation. And once I do that, I then get my final equation that I'm going to start plugging in values in. Be careful of the units that it's giving you and the units that it's asking for. In this case, I was given a pressure value of initial pressure in millimeters of mercury, and it specifically asked for atmospheres. If it hadn't asked for atmospheres specifically, if it had just said, what is the new pressure of the system, then I could have stopped right here, because millimeters of mercury is a perfectly legitimate and acceptable unit of pressure. But since they specifically asked for atmospheres, I had to go the extra step and do that conversion. Watch your sig figs. The 760 millimeters of mercury, or 760 torr, it is not an exact number, but we do treat it as if it were one, because we don't want to get in the habit of thinking that only has 2 sig figs, because the known value for that is much more precise than 2 sig figs. So we treat it as if it were an exact number. So our sig figs is determined by the other values in the problem. And that's how we use the combined gas law to solve for one of the variables, one of the properties of a gas, either before or after a change in conditions. We don't use the combined gas law for chemical reactions. All right.